chapter 4, we're going to be in 4.1. We're going to talk about an introduction to randomness, probability, and simulation today. So today we're going to talk about long run, what probability means in the long run. Talk about how to predict another probability based on what's going on, based on a series of events. And then we'll talk about how to to actually perform a simulation based on a probability. So, right, what is chance? Chance is probability, right? So the chance of something happening, right? So probabilities are always between 0 and 1, and they describe the amount of outcomes that are successes after a very large number of repetitions, right? You understand, and you probably learned this a long time ago, that a probability, right, is your successes divided by all of our possible outcomes. And we're really going to look at what this means. This is a theoretical probability. What this means over a very large number of repetitions. So, right, if it never happens, it has a probability of 0. If it absolutely did happen, it has a probability of 1, right? Half the time, probability of 0.5. All makes a lot of sense, right? Let's talk about the law of large numbers, though. It says that, right, like, for instance, flipping a coin, right? If we flipped a coin 5 times, right? I'm sorry, let's go 6. If we flip the coin 6 times, chances that every time I flip a coin 6 times, I get 3 heads and 3 tails is extremely low, right? It's not going to happen, right? We know that the probability of getting a heads or a tail is 0.5, right? So you would expect that you would get tails half of the time and heads half of the time as well. Now, if we did that just a small amount of times, chances are that's not the result that we're going to get. But the law of large numbers tells us that if we flipped a coin 1,000 times, it should be the case that roughly half of them are heads and half of them are tails, right? So if we do some probability event repeatedly, right, the actual probability, the actual number of results that we get should get very close to that theoretical probability that I told you about, right? Yes. All right. So we're going to model probabilities using a simulation, all right? A simulation. And we're going to go through an example of this here in just a minute. These are the steps that you would want to follow. Okay, so actually, let's go ahead and put this all to use. I think that with an example, things are going to make a whole lot more sense. So let's look at, will the train arrive on time? New Jersey Transit claims that its 8 a.m. train from Princeton to New York has a probability of 0.9 of arriving on time. Assume for now that this claim is true. Explain what probability 0.9 means in this setting. So it means that if it means that we expect 9 out of 10 trains to arrive on time. Doesn't mean that they will, right? It could be different from that value, but this is just kind of what we expect. You cannot say that it means that 9 out of 10 trains will arrive on time, okay? You got to use this word or something like that. You can't make a definite statement about that because these are probabilities, right? They're not always going to happen the way that we think they should, right? Our theoretical probabilities won't always match our actual probabilities, like in the coins, right? We would expect 1 out of 2 to land on heads, but that's not always going to be what happens. So the 8 a.m. train has arrived 5 days in a row. It's arrived on time 5 days in a row. What's the probability that it will arrive on time tomorrow? It's going to be 0.9. Okay. It's important to note that the fact that we've had a consistent amount of arrivals, it doesn't mean that the next one is going to come on time. Okay. And let's explain. 0.9, because not you, but the train is just as likely to arrive on time. Regardless of previous successes. Sorry? All right, and now for the tricky part, let's do a simulation. All right, so we've got a businessman. He takes the train at 8 a.m. to work 20 days a month. He's surprised when the train arrives late in New York on 3 of the 20 days. Should he be surprised? So let's carry out a simulation and estimate the probability that the train would arrive late on 3 or more of the 20 days. All right, I am actually going to perform the simulation. We're doing this, okay? We are doing this. Let's do it. Okay. All right, here we go. So our probability is 0.9. So we expect 1 out of 10 trains to arrive late. So this is what I'm going to do. I'm going to assign 1 through 9 as on time, okay? And 10 as late, okay? Then what we're going to do is we're going to put rand int, we're going to use our rand int function in our calculator to go 1 to 10. Let's do it 20 times, okay? That's what this command is telling us. And we'll count how many times 10 occurs, okay? So let's count how many times 10 occurs, right? That's going to simulate a late train, okay? How many times 10 occurs? So this is a late train. All right, let's go to our calculator and do this. And we'll see how likely it is. So this is just by chance, right? Got nothing to do with trains. We're just randomly picking numbers. If we were to just randomly pick numbers, how many times would we expect to get the number 10, which represents a late train? Let's do it. So I'm going to hit math. I'm going to go over to probability on my calculator. And I am going to hit rand int. My lower is 1, right? I want to go from 1 to 10. Let's go ahead and do that 20 times. And I'm going to count how many 10s we have. Okay. So there's 110. I'm just going to make some notches. 110. Mm. Not sure what just happened there. Whoops, sorry. I have the pen in my hand. It doesn't really work very well when you do that. Why it won't let me go over to the rest of the values is not cool. Okay, I had to get a new set of numbers because it wasn't cooperating. But let's count how many 10s we have. There's 1. And then as we scroll over, now it's working. Let's see. Only 1. So 1 out of 20 times we got that. Okay. So a 10 occurred. One out of 20 times in our simulation. So I would say that it's pretty unusual for that to have occurred. Based on our simulation. Let's talk about it in context. It seems unusual for the train to be late. That many times. All right, but let's go ahead and do it again. Let's see how often we would get 3 out of 20. Let's do it again. So I can just go up here, hit random again. And we've got 1 again. And let's see if there are more. 2. So this time, 2 out of 20. And the idea of the simulation is you continue doing this and just see how often do you get as many as 3. This next one is 1 out of 20. It's not going to be common at all. 1, 2. Ooh, this one's promising. 3. There's 1. So based on the simulation, it seems fairly unlikely that you would get 3 out of 20, right? That's only happened so far 25% of the time. We do it again. There are 1, 2, 3, again, 4. Ooh, I might be wrong. So now we've got 4 out of 20. Zero. Let's keep going. Let's see. Now that we got that 4 out of 20, I'm like wondering if my, okay, there's 1, 2. Maybe we'll do 10 of them. Just so that we can get a look at it. 1, 2, 3, 4. Oh, it might not be actually unlikely. Now, 1, 2, 3, 4, 5, 6, 7, 8. Let's do 2 more. I might have jumped the gun on that one, just looking at one result. 1, 2, 3. Another one. And now we have 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. And I'm probably going to have to change my answer. Huh. 0. Last one was 0 out of 20. So how many times did we get a result as extreme or more as what he experienced? There's 1, 2, 3, 4. So 4 out of 10 times is a 45% chance. So I am going to have to change that answer because it actually occurred in 4 out of 10 simulations. This suggests that it is not unlikely. All right, and that's much better, right? We want to do these repeated simulations. If you look at just one simulation, we might not get the full picture. But if we did 10 different simulations, we find that this isn't actually very unlikely to occur if it was just happening by chance. Okay, so now they actually did a simulation, right? And this dot plot shows the number of days on which the train arrived late in 100 repetitions of the simulation. So they did what we did, and instead of doing it 10 times, they did it 100 times, okay? And found that there were 3 or more late arrivals a bunch of times, like a lot, right? In fact, I don't know, I guess I can count the dots, right? 30. So 30 30 had 3 or more late arrivals. So that puts us at a 30% probability that if you were just going off this by chance, that that you would get a result as extreme or more extreme than this businessman experienced. So we estimate that we would get a value of 3 or more %30 of the time. You should not be surprised. So he should not be surprised that the train was late 3 times. Awesome. All right, so there it is, 4.1 in a nutshell. We did all of these things. Hey, thank you so much for watching, for taking notes, for being here, for being yourself, for smiling. Guys, I hope you're having a wonderful day, and if not, I hope it gets better. Take care of yourselves.